Hello, my amazing students. This is Mrs. A, and I am here with 9.6 of Intermediate Algebra, and we are solving radical equations. So I have some problems here for you, and we're going to solve radical equations by squaring both sides. Okay, so we're going to go through a step process. We're going to isolate a radical, square both sides, and then simplify. Sometimes as we get to more complicated problems, we will have two radicals and we may have to isolate them twice, okay? So we're going to isolate this one. We've got this one all by itself, so we're going to square both sides. Always whole sides, never individual parts. So the square root of x squared gives me just the x that's under the radical. And then 7 squared is 49. So x is 49, and we have solved that very simple equation. If we plug 49 back into the original equation before it was squared, we get the square root of 49 is 7, and 7 equals 7, which is true. Okay, so then we look at the second problem. And we have the square root of b minus 8 is equal to 2. So we already have a radical isolated, so now we will square both sides. And when we square the radical, we get the part that is under the radical, the radicand, okay? And when we square the 2, we get a 4. So we're squaring both whole sides. And then, since we want to get to b, we're going to add 8 and add 8 to the other side. And we're going to get b is equal to 12. Okay, so now to check it, we will plug b is equal to 12 back in here for the b. And if we plug a 12 right there, we get 12 minus 8 is 4. And the square root of 4 is 2. And there was a 2 on the other side. So when we check it, we're doing it without back into the original equation. Now, those two worked out just fine. We squared them, we solved them, and then we plugged it back in. When we solve problems with radicals and we square both sides, sometimes we can get extraneous solutions, and that's just a big word meaning extra solutions. And they are solutions that do not solve the original problem. Now, I'm going to show you a little demonstration about why this happens. So I'm going to start with a false statement. I'm going to say that 5 is equal to negative 5. And you're going to say, well, no, Mrs. A, 5 is not equal to negative 5. That is not true. But if I took that not true statement, that false statement, and I squared both sides of that equation, then I get 5 squared is 25. And over here I get negative 5 quantity squared, which is negative 5 times negative 5, which is also 25. So starting with a false statement, I squared both sides, and I got a true statement. 25 does equal 25. So that's just a demonstration about how squaring both sides can give you a false solution. All right, so when we use this method to solve a radical equation, we must always plug the solution back into the original equation, because when we square both sides, we will always get every possible solution, and sometimes we will get extra solutions. So let's do this one. When I do this one, I'm going to subtract. I'm trying to get the radical by itself on one side. That's the first step. So I'm going to subtract the 7 and subtract the 7. And now I'm going to get the square root of w plus 3 equals negative 4. Okay. Now, looking at that right now, I realize there's something wrong here, because we have already said that the square root, when we see that sign on a radicand, we see it, it's in a book, it's on a test, it's on a written piece of paper, it's already there. we know that means the principal square root. That means it's the positive square root, and I have it set equal to a negative number. So I already know this thing is not supposed to have a solution. There is no number that when I take the square root of it, the principal square root will give me a -4, because the principal square root should always be positive. But I'm going to go ahead and follow the process. I'm going to get a solution, but when I plug the solution back in, it's not going to work. It's an extraneous solution because the original has no solution. Okay, so now I'm going to square both sides. And by the way, I want you to do this if you do get a problem that has no solution. I want you to go through the process and show me that you got what was supposed to be a solution, but you found out it was an extraneous solution. All right, so we're going to square both sides. When we square the radical, we get the w plus 3 that's underneath it. And when we square the -4, we get a 16. Okay? So w plus 3 is 16. We're going to take away a 3. We're going to take away a 3 from the other side. And we're going to get w is 13. Okay? So that looks like that would be the solution. But then when I plug 13 back in, I get 13 plus 3 is 16. And the square root of 16 is +4. And then this one is a -4, and they do not equal each other. Okay, so 4 does not equal -4. Therefore, back in the original equation, it is not a solution. It was only a solution of the squared equation. All right, so this is a good example. This was not a solution. It was an extraneous solution, and although it solved the squared equation, it did not solve the original. We have to cross it out, and the answer would be no solution. Okay, so here we go with another equation. Right, we're trying to get the radical by itself. So we're going to add 2 to both sides. We add 2, and we add another 2 over here. So now we get the square root of 2y plus 4. The 2's go out, and on the other side I get a y plus 2. Okay, now this one very well could have a solution. We don't know. We're going to have to go through the process. So now we're going to square both sides, never individual terms. Square whole sides. When we square the radical, we just get 2y plus 4. When we square a binomial, we have a pattern for that. Remember, the pattern is, let's see if I got a place to write. I'm going to write it down and then I'll erase it. A plus b, quantity squared, is equal to a squared plus twice ab plus b squared. Way back in our polynomial chapter, we were taught this factor. Now, if you take a plus b and multiply it by a plus b, this is what you get when you FOIL it. Okay, so remember, I always say the first term squared, the product of a and b doubled, and the last term squared. So that's the formula that we're using. This is the pattern. So now we're going to erase that, and we're going to square this side. Okay, so since it's a binomial squared, it's going to be the first term squared, the product 2y doubled. So 2y doubled would be 4y, and the last term squared. So now we have two sides of the equation. Notice that both sides of the equation have a 4. I can cancel those 4's because they're on two different sides of the equation. Now, notice that I have a quadratic equation. When I have a quadratic, a y squared term, I want to get a 0 on one side. So I'm going to subtract the 2y from both sides. Okay, so when I do that, I get a minus 2y and a minus 2y from the other side. And my result is going to be what? This goes to 0. And I'm going to get y squared minus 2y is 0. So I'm going to erase this so we have a little bit more room here. Okay, so y squared minus 2y is equal to 0. Okay, that's what I get when I bring that all over to one side. Can I factor that? I'm going to bring out a y and a y minus 2 equals 0. So by my zero factor property, I've got a product equal to 0, so each part will equal 0. So y equals 0 is one solution, and y minus 2 equals 0 is the other one, or y equals 2. Okay, so now that I've got my two proposed solutions, I've got to go back and find my original equation, which I just erased. Okay, so let me find that again. All right, so I'm going to give myself a little space. These were my two proposed solutions over here. So now I'm going to rewrite the original equation, which was 2y plus 4 under the radical minus 2 equals y. Okay, so I'm going back. That's what happens when you have such a small board, right? So these were my two solutions that I think are solutions, but now I have to check, are they real solutions or are they extraneous solutions? Okay, so I'm going to take the y as 0 and I'm going to plug it back into the original, which means that this y is going to become a 0 and this y is going to become a 0. Right, so 2 times 0 is 0, plus 4 is 4. So I have the square root of 4, which is 2, and I get 2 minus 2 is 0. Well, 2 minus 2 is 0. So this solution is a good solution. Now let's check the 2. So I'm going to replace the y's with a 2, and over here I'm going to replace this one with a 2. And now I've got a 2 times 2 is 4, plus 4. So I get 4 plus 4 is square root of 8. Okay, and square root of 8 is 2 square root of 2. Minus 2 does not equal 2. Okay, so 2 square root of 2 minus 2 does not equal 2. So this one right here is an extraneous solution. So I always have to plug them both back into the original equation. Okay, and then we have another one here. And this one looks hard, but it's really easy because there's a 0 on the other side. So remember, my first goal is to isolate a radical. And I need to get each radical on opposite sides. But since there's a 0 over there, I can just add this radical to both sides. And then I'm going to end up with the square root of 3b plus 4. And then this one's gone. And now it appears on the other side with the opposite sign. So 2 square root of b minus 1 is on the other side. So I just took it from one side and changed the sign and stuck it on the other. So now when I square both sides, oh, things just get really dandy because I squared the radical, and so I just get a 3b plus 4 on this side. And then on the other side, I'm going to square both parts here. So 2 squared is 4. And the radical squared just gives me b minus 1. So I wind it with 3b plus 4 equals, I'm going to distribute this through, 4b minus 4. Okay, well, I just have a linear equation, so I'm going to go ahead and subtract a 3b and subtract a 3b. And when I do that, I end up with a 4 equals a b minus 4. And then if I add a 4 to both sides, I end up with b is equal to 8. Okay, so b equals 8. One solution, b equals 8. Now, we go back up to the original to find out if b equals 8 is a real solution or an extraneous solution. So that means right here where I have a b, I'm going to plug in an 8, And over here where I have a b, I'm going to plug in an 8. Okay, so 3 times 8 is 24, plus 4 is 28. Well, the square root of 28 would reduce some, but I'm not worried about that right now, because right now I'm just checking to see if the equation's true. So then the other b was also 8. 8 minus 1 is 7. So I have minus 2 times the square root of 7 equals 0. Okay, so I have this little equation right here. Now, I'm going to look a little bit more at simplifying. Is the square root of 28 equal to 2 square root of 7? Because if it was the same thing, then when I subtracted them, I would get 0. If I take the square root of 28, I'm going to erase this right here to give myself just a little bit of room. The square root of 28 is the square root of 4 times the square root of 7. And the square root of 4 can become 2 square root of 7. And 2 square root of 7, take away 2 square root of 7 is 0. So our one solution was b is equal to 8, and b is equal to 8 is a true solution, not an extraneous solution. All right, students, let's go back to problem number 4. And here's problem number 4 again on the board. And we had it correct up until this point, okay? But I want you to see the mistake that I made, because I always go back and check the answers to see if I got them right, and I lost a sign. So we had it right here. We had it factored on my other board. When I set each factor equal to 0, I get y is 0, but I don't get y is 2. I get y is negative 2. Okay, so if you remember this one, we checked this one and it was right. But then when we checked a 2, which was not the right answer because we missed a sign, it did not work. But let's check and see if negative 2 works, okay? Because it should have been a negative 2. So negative 2 goes right here, and negative 2 goes right here. So let's just see if negative 2 works. So we get a negative 4 plus a 4 is a 0. Okay, square root of 0 is 0. So 0 minus 2 is negative 2. And on the other side, I have a negative 2. So the solution y is negative 2, which is what that should have been, does work and does check. And I'm very sorry for that mistake. All right, so now we're going to start with problem number 6. And this one just says square and simplify. So we're going to take this and square it. And remember, we're using our formula, a plus b quantity squared. Anytime we square a binomial, it is a squared plus twice ab plus b squared. Okay, so this is the formula that we will use over and over when we square a binomial. And notice that we're treating this whole radical like one term. So it's the first term squared, that's your a squared. The first term squared is going to be 36. This product between the first term and the second term, we multiply these together and double it. Okay, so that's your 2ab. Multiplying them together and double it. Now this is outside the radical. This is inside the radical. So when we multiply them together, we simply get 6 times the square root of r plus 1. And when we double it, we get 12 times the square root of r plus 1. So plus 12 times the square root of r plus 1. And then the last term squared will just give me what's under the radical. So the last term squared is r plus 1. So now that we have all of this, we look and say, are there any of these terms that we can put together? We have a 36 whole number and a 1. We can join those together, but we don't have another square root of r plus 1, and we don't have another r. So our final answer is going to be 37 plus 12 square root of r plus 1 plus r. Okay, now if we're going to do that in descending order of the variable, then we would put the r first, and then we would put the radical r, so 12 square root of r plus 1, And lastly, we would put the 37 if we were going to write it in descending order of the variable. And there you have problem number 6. Problem number 7 is going to have to be squared twice because we have 2 radicals that we're going to have to separate. So this is a double squaring here that we're going to have to work on. So remember, we isolate a radical, and we're going to keep this one on the left, and we're going to send this one over here with the 1. So we're going to add this to both sides. Square root of c minus 9, add square root of c minus 9 to the other side. This goes out. On the left, I now have the square root of c equals 1 plus the square root of c minus 9. Now I square both sides. Both whole sides. Okay? So now when I square the radical c, I end up with just a c. When I square a binomial, I'm going to treat this like it's one term. I end up getting my a squared plus twice ab plus b squared. So the first term squared is 1. This product doubled. Okay, so 1 times the radical is just the radical. Doubled is going to give me 2 square root of c minus 9. And then the last term squared is going to take off the radical, c minus 9. Okay, so now notice I still have a radical term left. So now I'm trying to get that radical term on one side by itself. But notice how cool this is. I have a c on the left and a c on the right that I can just subtract from both sides. So they cancel out. So now I've got a 1 minus a 9. So I've got 2 square root of c minus 9 minus 8 equals 0, because this went to 0. And 1 minus 9 is negative 8. Now, but I don't want to get everything on one side. I only do that when there's a quadratic, right? An x squared. But if I add the 8 to both sides, then I'll get the radical all by itself. So I'm going to add the 8, and I'm going to come over here and add the 8. So now I have got 8 on this side. So I'm just going to erase that and put an 8 right there. And over here I've got a 0 because they cancel out. So this is what I have now. Okay, so now I'm going to square both sides again. But wouldn't it be easier to do if I just went ahead, you see I have a 2 outside the radical and I have an 8. Can I divide both sides by 2? I'm going to do that. I'm going to divide this side by 2. I'm going to divide this side by 2. Okay, so now I've got 4 is equal to the square root of c minus 9. Okay, so now can I square both sides? It's a little bit easier. I'm going to square the left-hand side, and I'm going to square the right-hand side. Okay, 4 squared is 16, and the radical squared just gives me what's under the radical. So I have c minus 9 equals 16. If I add 9 to both sides, then I get c is 25. So my proposed solution is c is 25. So now let's see if c is 25 is a true solution or an extraneous solution. So I have to go back up here to the original equation. This was my original equation right here. Okay, so pretend this little line through there is not there. So I had the square root of c. So I'm going to put a 25 in here. Square root of 25 is 5. And then that's 25. 25 minus 9 is 16. The square root of 16 is 4. Is 5 minus 4 equal to 1? It is. So this c is 25 is a true solution, not an extraneous solution. All right, so now we're going to do the next one. And again, this one will have to be squared twice again, because we have 2 radicals that we're going to have to isolate one at a time. So to get this one isolated by itself, I'm going to add the square root of 3k plus 4 to both sides. Okay, so now my new equation will be the square root of 7k plus 8, this cancels, is equal to 2 plus the square root of 3k plus 4, because I added this to both sides. So now that I have isolated one radical, now I square both sides. So I square and I square. Whole sides, always whole sides. So now this one, because it's a radical squared, is just going to leave me a 7k plus 8. This one we're treating like a binomial. First term squared is 4. This product is 2 times the radical, but when I double it, it's 4 times the radical. 3k plus 4. And the last term squared, we'll just take off the radical. So the last term squared will be 3k plus 4. All right, so that's what I have now. So now I look and say, what can I do? Because I really want to get this all by itself on one side. I want to get everything else over to the other side. Okay, so notice that I have a 4 plus a 4. Well, 4 plus 4 is 8, and on the other side I have an 8. So can I cancel the 8 with the 4 plus the 4? So now, a little bit simpler, I have a 7k equals a 4 square root of 3k plus 4 plus 3k. But again, I want to get this radical all by itself. So I'm going to subtract the 3k and subtract the 3k from that side. When I do that, then this one's going to disappear because they cancel. And this one's just going to become 7k minus 3k is a 4k. So we're going to write a 4k there. But then look how cool. I've got a 4k is equal to 4 times the radical. Can I divide both sides by 4? And when I do, both of those 4s are going to cancel out. I divided by 4, I divided by 4. So now this is what I've got. Now I have my isolated radical. Now I'm going to square both sides. Okay, so now I end up with k squared. And then on the right, when I square the radical, I just get what's under the radical is 3k plus 4. Okay, now this one is quadratic. Because it's quadratic, we want to get everything on one side and a 0 on the other. So I'm just going to subtract all of this and bring it to the other side. And I get k squared minus 3k minus 4 equals 0. Now, look at that. Does that factor? All right. And it does factor. I'm going to borrow another board here for just a second. We'll just use the bottom part of this board. Okay, so I've got k squared minus 3k minus 4 equals 0. If I factor it, k minus 4, k plus 1, does that FOIL to give me my polynomial that I desire? Okay, I've got k squared, a minus 4k, and a plus k. It gives me my negative 3k and then a negative 4 on the end. So it does work. So now what are my two proposed solutions? I've got a k minus 4 equals 0 or a k equals 4. And I have a k plus 1 equals 0 or a k equals negative 1. Okay, so we have two solutions that we need to check. So let's take those two solutions. K is 4 and k is negative 1. K is 4 and k is negative 1. And we're going to go back up here to, see, I wrote those down, my two proposed solutions. I'm going to go back up here. I'm going to erase this. And I'm going to get back to my original equation right there. Okay, so now let's try k is 4. If I plug in k is 4 over here and k is 4 over here, let's see what we get. 7 times 4 is 28. 28 plus 8 is 36. So I get the square root of 36 is just a 6. Okay, so now 3 times 4 is 12, plus 4 is 16, and the square root of 16 is 4. Is 6 minus 4 equal to 2? It is. So this one right here is a good solution. K equals 4 is a good solution. So now let's check k is equal to -1. So instead of plugging in a 4, we're going to plug in a -1 for our k and a -1 for our k, and we're going to check that solution. 7 times -1 is -7, plus 8 is 1. So the square root of 1 is 1. Okay, so then I end up with 3. 1 times 3 is 3, plus 4 is 7. So I get 1, oh, excuse me, that's a -3. That's a -1 times a 3. -3 plus 4 is 1. Square root of 1 is 1. So I end up with 1 minus 1 is 2. 1 plus 1 is 2. Not 1 minus 1 is 2. So this one did not work. Therefore, I cross out the k is -1. That's an extraneous solution. But the true solution is k equals 4. Okay, so now we're going to say what happens when we have something like cubed roots. Okay, now remember I told you in class we would not have a difficult cubed root problem. But notice that this one's an easy one because it's got a 0 on the end. So basically we're going to do the same thing. We're going to isolate our radicals. To get this radical by itself, I need to send this radical to the other side. So I'm going to add the 3 cubic root of the radical to both sides. And so I'm going to wind up with 2 cubic root of 5k plus 2 equals positive 3 cubic root of k plus 3. So I basically sent this to the other side with the opposite sign. Now that I have both of them isolated, I can cube both sides. Just like I can square both sides, I can cube both sides. So now 2 cubed is 8. And the cubic root cubed is going to give me 5k plus 2. And on the other side, 3 cubed, this is your index here. That's awfully big. Let's make him smaller. Okay, 3 cubed is 27. And the cubic root cubed is going to give me the k plus 3 that's under the radical. So this is the equation that I get. And I'm going to end up getting 40k plus 16 when I distribute that. And 27k plus 81. 27 times 3 is 81. So this is just linear. So we really want to get everything on one side of the equation. So I'm going to borrow another board here. Okay, so if I get my k's on the left, I got 40k, take away a 27k. So I'm going to subtract the 27k from both sides, and that's going to leave me with a 13k on the left. Okay, and then I want to get the 16 over on the other side. So subtract 16, and 81 minus 16 is going to be, okay, when we subtract, that's going to be a 65. Yep, 65. So we're just going to write 65 here. Okay, so my equation simplifies down to here. So now if I divide 65 by 13, I get 5. 5 times 3 is 15, carry your 1, and 65 divided by 13 is 5. So our proposed solution is K is 5. Okay? So I go back up to my original, which was on this board, and I plug in K is 5 to check and see is it a real solution or an extraneous solution. So I plug in a K is 5 here, and I plug in a K is 5 here, and I get 25 plus 2 is 27. The cubic root of 27 is 3. So I've got 2 times 3. Okay, minus, now I plugged in a 5 here. 5 plus 3 is 8. Cubic root of 8 is 2. 3 times 2 is 0. 2 times 3 minus 3 times 2, yep, that's 0. Now, realize that when we cube both sides, we don't have the same problem with extraneous roots that we do when we square both sides. Because when we cube both sides, we do not mess with the sign. A negative number cubed is still a negative number, and a positive number cubed is still a positive number. So cubes and cubic roots don't mess with signs in the same way that squaring something does. So we should not have extraneous roots when we cube both sides. So that is a cubed root problem, and its solution was good, so we would say the solution was 5. And the last one we're going to do is one more of the harder, more difficult square root problems. Okay, so we're going to square both sides because we already have one radical isolated. So we're going to square both sides, whole sides. When we square the radical, we get 5k plus 1. When we square the other side, we get the first term squared, which is going to be just what's under the radical. This product, which is just going to be the radical, doubled 2 times 4k plus minus 3. And then the last term squared is a plus 1. I'm going to squeeze a plus 1 right there. Okay? So plus 1. So now notice that I have a plus 1 and a plus 1. So I'm going to take those out of there. They cancel. And I've got a 5k. On the other side, I've got a 4k. I'm trying to get everything on the other side except for this radical, right? So I'm going to subtract the 4k from both sides. So now I've got k equals negative 3 plus 2 square root of 4k minus 3. But I really want this negative 3 on the other side, so I'm going to add a 3 and add a 3 over here. So now I get a k plus 3 equals 2 square root of 4k minus 3. Okay, so I'm going to leave my equation up there, but I'm going to go ahead and give myself a little bit of room to work this last problem here. Okay, so now I'm going to square both sides of this equation. When I square this side, I have a binomial that I'm going to square. So I'm going to have the first term squared, the product doubled, and the last term squared. Okay, when I square this side, I'm going to have... My daughter's trying to get out of the door. Okay. Okay, here, let me pause the video. All right, so now we're going to square the right-hand side. So 2 squared is 4. And this one squared is going to bring it out of the radical. So 4k minus 3. So now when I distribute this, I'm going to have 16k minus 12 on this side. And k squared plus 6k plus 9 on this side. Now, because I have a quadratic, I want to get everything on the left with a 0 on the right. Okay, so we're going to do that. We're going to subtract a 16k from both sides. And we're going to add a 12 to both sides. So now what do I have left? I have a k squared, a minus 10k, a plus 21 equals, and all this goes to 0. Now, will this factor? Well, it sure will. I'm going to have a k minus a 7 times a k minus a 3 gives me a k squared minus 10k plus 21. So since I set them both equal to 0, I have two proposed solutions. K is 7 and k is 3. Okay, so I've got to check those two solutions. So to plug in the 7, I go back here. If k is 7, I get 5 times 7 is 35 plus 1 is 36. Remember, we're back to our original, so I'll take off those squares. The square root of 36 is 6. Okay, and when I plug in the 7 up here, I get 4 times 7 is 28. Minus 3 is 25. The square root of 25 is 5 plus 1 is 6. 6 does equal 6. So 7 is a good solution. Okay? And 3. We check 3. If we plug in the 3, we get 3 times 5 is 15 plus 1 is 16. Square root of 16 is 4. Okay, so then I'm plugging in the 3. 4 times 3 is 12. Minus 3 is 9. Square root of 9 is 3 plus 1 is 4. And I get 4 is equal to 4. And I have two good solutions, 7 and 3. And that is the end of 9.7. And this is Mrs. A. And may God bless your day.